two talks will be entertaining, as it should be after lunch, because there will be lots of variations on variations. And the first one will be variations on the expression problem.
Thank you. Can you hear me? Okay. Right, so I want to talk about extensible variants. I want to start out by telling you a little bit about why we might care about extensible variants in the first place, sort of what kind of language problems we solve. So for those of you familiar with the expression problem, this will be sort of the expression problem, but backwards. And then I want to tell you about a particular design I have that addresses the sort of extensible variant space, a couple of implementations of that design, and hopefully what I was able to learn by comparing these implementations with different implementation techniques and comparing them to sort of a gold standard of how we might implement extensible variants. So in one sense, this is another encodings paper, but hopefully it's a comparative encodings paper. You can sort of learn something from building these encodings beyond just the existence of the encodings themselves. But let's sort of start out by talking about why we might want extensible variants. So I work on the implementation of a language called Habit, among other things, and when I started building the compiler, the front end looked something like this. I had some sort of big conceptual passes like parsing and type inference, and I had some files called like parsing.hs and typeinference.hs. But one of my coworkers had been trained in Indiana, and so he said, no, this is be these will become unmaintainable very quickly. You should build the front end of your compiler like that. So that might seem a lot more complicated, but the thing is that most of these passes are actually very, very simple, right? So previously I said desugaring, right? Well, Habit is a Haskell-like language. It has a lot of sugar in it, right? There were a lot of things that happened in that file. Whereas in this case, you can actually sort of see, like here's where infixity is handled, right? We don't need to worry about, either the state that's needed to sort of resolve infix expressions or sort of the details of infixity at any other point in the compiler. So this allows us to sort of break down, the different features of the language, handle them one at a time in sort of much more compact, much easier to understand passes. So this is sort of NanoPass, but without any of the support for that you would get, with the NanoPass framework and scheme. But we're doing this in Haskell, right? So we wanted to not just be able to structure the compiler this way, but gain something from typing. So the question is, how can we type these individual passes in a way that sort of gets the compiler to do our work for us? So sometimes it was actually really easy, and I'm going to sort of elide some details on these slides, but for kind inference, for example, we sort of have an incoming AST in which all of our type identifiers are just unadorned strings, basically. And we do some kind inference, and we look at a bunch of declarations and such, and then we can produce an AST in which all of our type identifiers have sort of sprouted kind annotations, right? And this is very easy to actually parameterize in the type signature. And now if I've sort of, as usual, forgotten some recursive case where I ought to be sort of recursively applying some substitutions, that'll show up in the types, right? So I can sort of get the compiler to both document, or I get the type system, to both document what I'm doing and check that I haven't missed any cases. On the other hand, there are a fair number of times this sort of didn't work great, right? So here's what I ended up doing for infix grouping, right? I have sort of expressions on the way in, and I have expressions on the way out, and I've learned nothing, right? I haven't documented the past behavior. I can't check the behavior. This isn't doing me a lot of good. The reason for that is that sort of the change here isn't easily parameterizable, right? There's sort of one case in an expression in the AST that I'm sort of removing in the course of this pass, but that's not something that sort of easily pops out as a parameter of the type. Right? So obviously I could have sort of defined lots and lots of types, right? So I could have sort of expressions that include the infix constructor and expressions that don't include the infix constructor. I could define these ASTs. I could very nicely define, get this pass to type. But now there's going to be sort of a lot of additional effort that comes along with all of these versions of the AST that I have to build. So for one thing, these passes, are supposed to be nice little modular pieces of code that I can move around, reassemble, add new ones, take them out. But now sort of that structure has been sort of encoded in this nest of ASTs. So anytime I want to change the structure of the compiler, I have to go rewrite a whole bunch of ASTs. Anytime I want to add a new thing, even if I want to add a new feature here, and I want to desugar it here, and that's all I think I want to do, every point between here and here, I've got to sort of go change my AST type to sort of add that in and then not worry about it. So there's a lot of typing to make this piece of typing work. What I'd really like to, thank you. What I'd really like to be able to do is something like this. So this is my sort of idealized case. I'll sort of work my way back to it a couple of times in the rest of the talk. What I'd like to say is I'm going to come in with some expression type. It's going to be a functor, so there's going to be some fixed points running around. You can sort of ignore that sort of line noise. So I've got some collection of types coming in, some collection of expressions. I'm going to do infix stuff. And what that means is that whatever I get out it's going to have all the stuff that E had, but it's no longer going to have the infix case. Right? Now, I can't just make infix expressions go away. Poof. I need sort of something to turn them into. So I have sort of a side condition on this. It says, well, I don't care what else is in E. It can have cases, it can have branches, it can have, all sorts of exciting things. But it best have applications because I wouldn't want to turn an infix expression into sort of a series of prefix applications. So this is sort of the type that I really want to have for my infix grouping pass, right? It captures the behavior of the pass precisely, what it does, what it doesn't care about. It doesn't sort of interfere with reordering or AST changes, right? I can sort of compose these in different orders so long as the constraints all hold. And in fact, it allows me to sort of, I didn't mention this, but it allows me to sort of very nicely write generic, let's say substitution application or free variables functions that I can apply at a number of different points in my AST. So this is sort of the goal. Like I say, this is sort of the expression problem, but in reverse. I'm taking cases out instead of adding cases. And this is what I want to accomplish over the course of the remainder of the talk. Okay, so I call these extensible variants, right? So what do I mean? I mean, I have these variant types, and I have these sort of extensions of them. So what do I know about variants, right? Well, a variant is sort of a generalized coproduct. So we'll start with what I know about coproducts. Those of you who know me will know this slide is sort of very foreign to my normal way of presenting things, but this is sort of what I know about coproducts. I know that A plus B is a coproduct of A and B. If, on the one hand, I can sort of stick A's and B's into A plus B. And on the other hand, if I have sort of behavior from A to C and from B to C, I can sort of put that together with this operator type to build something that goes from A plus B to C, right? This is sort of my nice binary coproduct case. I think of variants as generalized coproducts. So what does that mean? Well, it means I'm going to take all my pluses and turn them into sigmas. So I have a bunch of things in the middle here, a bunch of AJs, some J's around. And I can talk about some collection of those, so assume that the I's are a subset of the J's. Right? And if I have sort of something that's in a smaller collection of sum-ands, I can stick it into a bigger collection of sum-ands, right? Then I can also sort of talk about all the things in AJ that aren't one of these I's, and I can similarly build this mQuery n turn that sort of takes behavior for the I's, behavior for the not I's, and builds behavior for all the J's, right? So this is my sort of idealized picture, okay? It doesn't actually exist in programming language that I know of. So how have people looked at this in the past? Well, sort of one common approach, I'm going to sort of take it as a gold standard for part of the talk. It's a little bit different, but is to sort of look at row typing. So, stuff I was going to talk about. Talk about row typing. So row typing is sort of a labeled variant of that picture, right? So we don't just have arbitrary sum-ands, we have labeled sum-ands. Otherwise, a lot of the picture sort of starts out the same. I have a bunch of labeled sum-ands. The syntax I've picked here is mostly that of Gaster and Jones, but there are lots of row type systems, and you can probably pick the one you want. The biggest difference here is that these labels sort of make this diagram like not as symmetric, right? So here I have this kind of nice thing where basically these two sides are just two collections of terms in the bigger sum, right? Put them either way you want. Here I've got these labels running around, so these two parts of the diagram are kind of incomparable now, right? Over here I just have a sort of a bare A. Over here I have a sum. So the diagram isn't symmetric. On the other hand, I do still have this nice property that I sort of didn't talk about on the previous slide, that because this is inbuilt in my programming language, I don't have to sort of worry about reassociating. So you can sort of say that these sums are sort of associative and commutative and such not, and have that sort of built into my notion of typing, right? So that's sort of one approach to this. I'm going to sort of encode a different approach, and then try to compare it to this and sort of say, well, how well does our encoding do when we compare it against something that's sort of like built into programming language is sort of the gold standard? Okay, so what's my approach? Well, I'll start out by sort of saying I'm going to use a bunch of binary coproducts, which I know how to define, and use them to build up arbitrary coproducts. And then I'm going to sort of try to overload my injection and branching things to behave as if they were sort of nice, n-ary coproducts. Right, so I'll say I have something, we've got functors, sorry. So I've got some big collection of things G of E here. And I've got some sort of subcollection of those things F of E. And if F is a bunch of cases that appear in G, then I can sort of inject F of E's into G of E's. So far, so data types a la carte. But now I want to finish the picture, right? So what's left? Well, I have sort of the remainder over here. So this is sort of a type function from all the things in G that aren't in F. And again, if I have sort of behavior from the things in F and behavior from the things not in F, I can use that to build behavior from the things in G. Right? So this is sort of what I've attempted to implement in this paper. Cool? Okay, so we restore the symmetry. We have sort of these arbitrary binary coproducts that we have to sort of work with somehow. So what have I done, right? So I've sort of given you this motivation for my design for how we might do extensible variance. I haven't talked a lot about extension, but you'll notice they're sort of very generic things. So, F could be a type variable, G could be a type variable. Extension sort of comes for free once we're building on top of a framework of binary coproducts. So I've sort of presented this design. Hopefully I've motivated a little bit. I've sort of told you why you might want to use it. So what have I done? I've sort of implemented this twice. So the first time I implemented it with instance chains. So instance chains are an idea that Mark Jones and I presented at ICFP a couple years back. They're a really cool, neat way to sort of define new type classes, and a more interesting way to sort of define type class instances. If you have my laptop, you can try them today. If you don't, it's a little trickier. So in addition, I sort of took my instance chain implementation and I was able to translate it into, I've written type functions, I probably should have written type families, into closed type families. Right, so sort of how do we take this sort of cool feature that I think is great and explain it in terms of closed type families. And the advantage to that, of course, is that you can actually play with that today even if you don't have my laptop. So I've got these two implementations of the same idea, and now I want to try to sort of compare those to my gold standard and to each other. So the question is sort of, are these encodings as expressive as something we could do with row types? Are there expressions that will type with row types that won't type with the encodings? And similarly, can we use these encodings to learn something about the implementation techniques? Obviously, I think I can translate my implementation from one approach to the other. Do we learn anything about the relative expressivity of these things? What we might want to use them for by looking at the sort of point that's in the intersection of the things they can express. Right? So I'll sort of spoil the answers, and then I'll hopefully talk about a little bit of code. In the first case, the answer is, sort of the politician's favorite answer, yes, but. Yes, anything that we can encode with row types, we can sort of translate into either of these encodings, pretty much. There are two sort of buts to that. The first is that these are encodings, they're not built into the language, and that means there's a certain amount of syntactic overhead, right? So a couple of times I've said, oh, it says fixed, don't worry about that. Of course, when you're writing the code, you do have to worry about that. This is sort of to be expected with a lot of these encoding things. There's going to be some syntax. On the other hand, there's also what I sort of think of as being a bit of semantic overhead. And that is to say there are sort of terms that you can type with row types unambiguously. When you translate them into sort of either of these encodings or frankly any other sort of data types a la carte-ish approach you want to talk about, you have to sort of disambiguate some choices. You have to give the compiler a hint as to sort of how you expect some variables to be instantiated. I think I've actually characterized those points fairly well in the paper. I'm not going to talk about it in the talk. In the paper, I sort of start to talk about a way that we might address that. It's not quite as simple as sort of saying, oh, we need to fix the language, because the fact is these variables are ambiguous. We can demonstrate that they're ambiguous, but sort of with suitable restriction, they can sort of hint that they might not be ambiguous. Second question, are the implementation techniques equally useful? Again, yes, but the instance chain code is a lot shorter. Okay, this is not a good thing necessarily. APL programs are really short. But I think that sort of looking at the difference between them can help to sort of maybe make some language design choices. So everybody will disagree with me, but the point here is that with the instance chains code, we're able to sort of simultaneously do type computation and instance selection. And that's a thing that sort of these examples suggest to me can be sort of usefully related. When we take these things apart and try to treat them orthogonally, we end up sort of repeating ourselves. There's work that we sort of have to do at the type level and then have to repeat at the value level. At least it might suggest that we sort of want roughly comparable features at both in sort of defining instances and defining type functions. Second, and I'm not going to be able to talk about this in the slides, but I've sort of put it up here to start a fight. My translation mechanism seems to break down as soon as you have more than one functional dependency involved. If you have one functional dependency, it's great, everything works. If you have two, read the paper. So I want to try to show you a little bit about how this works in some of the code, hopefully show you a bit of the translation and sort of motivate on the one hand how the translation works, and on the other hand maybe what we could learn from it. So I'm trying to build this picture over here. I have some base types. I need sort of some binary coproducts of functors. I need a fixed point. I need some classes. So again, I'm sort of simultaneously defining a type function minus, and then this branching thing at the value level. I'll show you some sort of code for these things in a bit. This is just trying to show you how this works. Builds this picture. So how would we use it? Well, I'm not going to talk about a full programming language. I'm going to talk about a very simple programming language. It has sort of three things in it: constants, multiplication, and squaring. Right? Maybe there are a lot of things I have to square, so this is a useful surface syntax, but I can sort of express squaring in terms of multiplication, obviously. So I might want to create a pass that sort of desugars squaring into multiplication. Here's the pass. Basically, we want to take an expression. We want to define sort of an option where we either say it's a squarey thing, do this code, or it's anything else, don't care, sort of do my default case. My squaring case is hopefully fairly simple. I sort of say, well, if I'm trying to square E, First, I need to rewrite any square things that appear inside of E. So now I have a square-free E prime. And then I multiply E prime by itself, and then I stick it back into the top-level type. If I have anything else, it's not a square, so I don't need to rewrite it, but it may have squares inside it, so I can rely on these things all being functors to sort of rewrite all the squares inside it. Right, stick these things together with my branching operator, deal a bit with these sort of ins. This is the fixed point constructor. Deal a bit with the fixed points, and I'm done. Right? Feed this into the type checker and it infers the following type. If I can fit this times case into E minus square, then this takes an E to an E minus square. Right? That's the inferred type. No type signatures I haven't put on the slide. That's sort of almost exactly the picture I claimed I wanted from the beginning of the talk. Right? These cases are obviously not entirely first class. Sort of, we want modular things. We want to be able to sort of manipulate these things freely. There's sort of some references to the recursion built in, but I can abstract that a bit further. If I sort of define these cases independently of the recursion, I can define a nice combinator that sort of fills in the recursive bits, and I have sort of a nice case construct. So obviously you can go a step further and turn this into algebras. Talk about this in terms of your usual fold. This is sort of maybe a little more general than folds, but sort of a lot of these data types a la carte sort of style things will build folds. That's just one step further from here. Right? Okay, so let's talk a bit about how this works in not a lot of time, so I'll probably have to skip over a couple of steps here. Instance chains sort of give you three things. They give you this sort of chaining of instances. You can sort of say prefer this one to that one, prefer that one to that one. They give me a notion of when things aren't true. I can say some F's are just not in some G's. And by putting these together, I can get a notion of backtracking. I can sort of say, hey, I can put F into G plus H if F is in G. I may discover that F's not in G. That's fine. Go back here, try the next case. I can put F into G plus H if F is in H. Maybe it's not there either, but there's still a third possibility. Maybe this thing is a sum, right? Take the sum apart, try to put the components individually into H. Right? Okay. So that's what I'm going to try to say about that. Skip the slide. When I sort of translate this to type families, I have to sort of tease apart sort of two components of what's going on here. On the one hand, I have proof search, right? That's the sort of backtracking process I just, sort of hand-waved my way through. And when I can do that and sort of figure out like which path through these instances I need to inject a particular thing into something else, maybe I have to use this case, and then that case, and then this case again, and then that case, and I'm done. Right? So I can think of that as sort of a witness or a proof. I can compute that at the type level. Then having computed sort of a witness of that at the type level, I can go in and use that witness to drive instance selection just using boring standard type classes. So how does that work? Well, I'll start out by talking about the proof search. I've grayed out the bits of the slide that don't have to do with proof search. I've also, because I skipped something, got a bit of noise in here, but these sort of additional constraints that sort of avoid some kind of arbitrary choices on the part of this class, but they're not terribly important. To translate this, I sort of want to build a type family that's going to compute sort of the path through this instance. So we'll sort of start out by creating some data types that represent the path through the instance. We're either at the end of the path, or we need to go left, or we need to go right, or we're stuck. You can do this with data type lifting. I'm sort of trying to avoid that many sort of language pragmas, but obviously some of this stuff could be expressed that way. And now I'm going to build a simple type function called into. F into G computes the path to insert F into G. Some of these cases are simple. Injecting F into itself is I'm done. That's the end of the path. I have a middle case here I'll come back and talk about, but if that doesn't work either, then I'm done. It doesn't work. It doesn't fit. Right? So this is just a standard, I guess, closed type family. The middle case is a bit tricky. So I sort of said we have backtracking search going on here, right? I might sort of start down this path, discover it doesn't work, sort of back up to this path. On the other hand, in the closed type families, I don't have backtracking search. I basically have to implement it. So that's what this is doing. It's just a truth table, basically, of the possibilities, extracted from this nest over here. So sort of the possibilities are either I can stick F into G or I can stick F into H. And these bits are accounting for this sort of disambiguation business. Down here, I have the truth table. So I can sort of say, well, if I can't stick F into either side, it doesn't work. If I can't stick F on the left, but I can stick it on the right, that's this Q, then we'll go right. If I can stick it on the left, we'll go left. And if none of those apply, it doesn't work. Right? So I've sort of taken the logic that was sort of encoded over here and sort of broken it out explicitly into this truth table. Out of time. With that, I can now define sort of an instancy thing, a standard type class that takes not just my F and my G, but also the witness, and on the basis of that witness, constructs the appropriate behavior. I can then tie this all together, invent some witnesses where I need them, and I get something that's got the original type signature that I wanted. If anyone's interested, this is not a Cabal link because it's exactly one source file. But if you go to this URL, there's a link that says sample code. You can play with this in GHC. And yeah, I'd be happy to take any questions.
So on slide 23, I might just be talking about a typo here, so sorry to waste the time, but you made sure that both the left-hand sides were nope, but only one of the right-hand sides was nope on the second to last line there. Shouldn't that be both, or it doesn't matter, I suppose?
No, because I sort of passed over a bit. You want to read the first column and the third column.
Oh, okay.
The second column and the fourth column are solving a different problem that I didn't have a chance to talk about.
Thank you.
Sorry. Yeah.
This is fantastic, but one thing I was looking for was the user experience for the compiler writer. So what does this end up looking like for them? Have you translated all of the habit compiler into this style? And what about performance in terms of raw tree traversal speed between native subtypes and the two approaches you mentioned?
Okay, so question number one, the user experience looks sort of like this. So yeah, so this is real code. You can compile it. So you can sort of, and you can do a little bit better. Maybe sort of avoid some of the noise to do with the fixed points and stuff by defining some combinators. The habit compiler is still written in Haskell, so I sort of haven't translated it to use this approach. Speed, I'm sure it's slower. I don't know how much slower, but sort of every place you might hope that you'd have sort of an n-way case split, I've sort of built a nested case split, and yeah, I'm sure there's a not insignificant performance penalty that I don't know what it would be exactly.
Thank you.
If I can follow on the user experience, that code looks very nice, but what if we have type errors? How did you compare these solutions?
Type errors. This is an interesting question. I haven't thought about type errors in a lot of detail. I mean, you frequently get sort of. I mean, you can get sort of it's sort of concrete instantiations. You can get sort of things that say I can't stick this into that. You know, I can't stick sort of a thing with apps into it and a thing that doesn't have apps in it. That's fairly readable. I don't know how it would compare to something like row typing where it was built in though, and I'm sure there's a certain amount of noise with the errors.
Thank you.
It's sort of a different way of slicing the problem, but when I've thought about this sort of issue, sometimes I think about making my AST type a GADT and then labeling each constructor sort of what phases it's applicable to.
Yep.
Did you look into that, and how does that compare?
So I guess the biggest the biggest distinction I make between my approach and that one is to say that in that approach, sorry, I was. My sort of intuition is that approach isn't quite as modular in the sense that you still have sort of a canonical AST that's going to have to include sort of all of your cases. Now, I mean, maybe that's reasonable for a certain number of applications, and in that case, it probably works out. I was sort of thinking of, you might want to sort of desugar a bunch of cases. You might be adding new forms that aren't in your Surface AST. Yeah, go ahead. Sorry. And in that case, I think sort of having a slightly more generic approach where you can sort of, you don't have to sort of have a single sort of type to rule them all, may be easier to work with.
Thanks.